Second derivative test for local max and local min. Theorem 5. Second derivative test for local extreme values. Suppose f double prime is continuous on an open interval that contains x equal to c. If f prime at c is 0, that means c is a critical value, and then when we take the second derivative and plug in this critical value into the second derivative and it's negative, then f has a local maximum at x equal to c, which would just make sense. First of all, when f prime is 0, we have a horizontal line tangent to the curve, and then f double prime is negative, means it's concave down, which would make sense that it is now a local maximum. Alright, number 2. If f prime at c is 0, again you have a horizontal line tangent to the curve, and f double prime at that critical value is positive, then f has a local minimum at x equal to c. And again here, where you see that it's concave up, where a horizontal tangent line occurs, then we see that it holds water, so it is a local minimum. Now, in number 3, if f prime at c is equal to 0 and the second derivative there is 0 too, then the test fails. So the function may have a local maximum or local min, or it may not occur even there. So when the test fails, then we go back to the first derivative test. Procedure for graphing y is equal to f of x. You identify the domain of the function and look for symmetries where if usually even powers of a polynomial will make it an even function, odd powers of a polynomial will make it an odd function. Number 2, take the first derivative and the second derivative. Number 3, find the critical points of f, if any, and identify the function's behavior at each one. Find where the curve is increasing or decreasing. Find the points of inflection, and if any, and determine the concavity of the curve. Number 6, identify any asymptotes that may exist. Remember, in section 2.6 we looked at limits where we were able to determine the vertical or the horizontal asymptotes of a function, or even a slant asymptote. Plot key points such as the intercepts, the points found in the critical points from local max, local min, or points of inflection, and then sketch the curve together with any asymptotes that may exist. Here are just the general shapes of different functions, like if you have a linear function, if you have a cubic, if you have a fifth root, you see how these are all odd functions and the general behavior looks like this. If you have powers of x to the n where it's even, like x squared, x to the fourth, x to the sixth, the general behavior looks like this, where we have seen from the previous slides that these functions are either concave up or concave down. They do not have any point of inflection. Some more functions of the rational functions of the form a over x to the n, like 1 over x, 1 over x cubed, again 1 over x to the fifth, and so on and so forth. The general graph or pattern of the graph would look like this. And if you just take the negative, it'll be reflected about the x-axis. If the power of x is even, then it will just be symmetric about the y-axis, and it'll remain above the x-axis because it's always positive and never 0. And then this is just the negative reflection when you put a negative in front. A good exercise is to determine what is the domain and range of these two graphs. Root functions like the cube root, the fifth root, etc. It would behave this way, and you can see that it has a point of inflection right there. And that's just the negative reflection. If you have an even root, like say the square root, the fourth root, etc., then it will be positive, and the domain would be 0 to infinity, including 0, because you can always take the nth root of 0. It remains above the x-axis, so you can also determine the range of this function. And the one on the right is just a negative reflection about the x-axis. When we have a polynomial function and then the zeros are factored, if it's a simple zero, that means, let me write a simple example of this function. Say y is equal to x minus 1 times x minus 3. That's what it means to have a simple zero. It does not have it's not squared or a higher exponent other than 1. And if you have a zero of odd multiplicity, let's say y is equal to x minus 5 cubed, then this is how the graph would look like. Or of course, if it's negative, then it's in this other direction. So you can see that a point of inflection occurs at C. And then if the zero of a function has multiplicity that is even, then say y is equal to x to the 4th. So here your C is 0. Say y is equal to x minus 2 raised to the 4th. Then 2 is a 0 of multiplicity 4. It's even, and so you have no point of inflection occurring around C. Sketch the graph of y is equal to x to the 4th minus 4x cubed plus 10. Okay. The basic solution of this function would be dominated by the highest degree, which is x to the 4th. Y double prime is equal to, okay, differentiating this again, we have 12x squared minus 24x. Set that, now when we take the second derivative, you plug in the critical values that we found when we took the first derivative. And y double prime at 0 is 0, so the second derivative test fails. Then we go back to the first derivative test. Okay, what about at x equal to 3? So you plug in 3 into the second derivative, and that's 12 times 3 squared minus 24 times 3, and that is equal to 36, which is positive. Therefore, if it's positive, remember that it's concave up. So when it is concave up, then you have a local min or local minimum occurring at x equal to 3. Since the second derivative test failed at x equal to 0, we might as well use the first derivative test to find out what is happening around x equal to 0. So the two critical values are 0 and 3. We already know that a local min occurs at x equal to 3. Okay, so using the first derivative test would tell us whether where the function is increasing or decreasing. So if there's a change of sign in the first derivative, then we will either have a local max or a local min. So let's test -1, and then between 0 and 3 we can test 2. And let's see, y prime at -1 would be 4 times -1 cubed minus 12 times -1 squared. Okay, this would be -4 minus 12 would be negative. So that means it is decreasing on the interval from minus infinity to 0. What about between 0 and 3? Let's test 2. So you take y prime at 2, so that's equal to 4 times 2 cubed minus 12 times 2, and this will still be negative. Okay, which means it is still decreasing on the interval from 0 to 3. So since there is no change of sign of the first derivative to the left of 0 and to the right of 0, that means x equal to 0 is not a local minimum or local maximum. And of course, if we want to test to the right of 3, say 4, y prime at 4, you can test that and see that this is positive. So it is increasing to the right of 3. And we've already verified that y double prime at 3 has a concavity there. It's concave up. So we know that we will have a local minimum occurring at x equal to 3. Okay, so the critical point 0, 10, that's just plugging in 0 for the x. We plug in 0 for the x here, so y is equal to 10. Then when we plug in x equal to 3 into y, we get y equal to negative 17. That is a local minimum. Okay. Now let's find points of inflection. When we set y double prime to 0, we see that x is equal to 0 or x is equal to 2. Now we're going to test for concavity. Okay, so there are two critical values for the points of inflection when x is 0 and when x is equal to 2. So we test, say, negative 1, we test 1, and then 3. Y double prime of negative 1, okay, y double prime at negative 1 would be 12 minus 12 plus 24, because when this is negative 1, then it becomes positive 24. So this is equal to a positive sign for the second derivative. Okay, between 0 and 2, we plug in y double prime at 1, and that is equal to 12 times 1 squared minus 24 times 1. That makes it negative. We see that there is a change of sign to the left of 0 and to the right of 0, so that means x equal to 0 is a point of inflection. Let's see what happens to the right of 2. We've already plugged in, we tested that at 3, y double prime is positive. So y double prime at 3 is positive. So that means there is a change of sign to the left of 2 from negative to positive. So we have 2 points of inflection occurring at x equals 0 and at x equal to 2. Now to plot those points, we already know that why this is not a critical point. It turns out, or it is not a local max or min, because it is a point of inflection. And then you plug in x equal to 2 into the original function to get the critical point for another point of inflection. Okay, here's just a summary of what we did. We looked at the critical points for possible local max or min, and we found that it's x equal to 0 and it's x equal to 3. We saw that to the left of 0 it's decreasing, to the right of 0 up to 3 it's decreasing, and then to the right of 3 it's increasing. That's why at x equal to 3 there is a change of sign from decreasing to increasing, making x equal to 3 a local minimum. right? So here we use the second derivative test to find points of inflection, and of course from the previous slide we saw that there is a concavity occurring at from negative infinity to 0. Then from 0 to 2 it's concave down, and then from 2 to infinity it's concave up. And this is just a summary of what is going on at the different critical values. And we can just look at all these based on the above tables. It's just putting these together, where it's concave up and concave down means at 0 there's a point of inflection, and then to the left of 3 and to the right of 3 there's a decreasing to increasing, means it's local minimum, and which coincides with to the right of 2 it's concave up. So that's why at x equal to 3 it's concave up there. Okay, so let's summarize what we did in our sketching the graph, how we got to this graph. First, we look at the basic function is the highest power that occurs for this polynomial, which is y is equal to x to the 4th. And the domain is all real numbers. We looked for critical values to find local max and mins, which means we set the first derivative to 0. Then we looked at the second derivative test for local max or min, and when it fails, then we use the first derivative test. Then we looked for critical values for the points of inflection by setting the second derivative to 0. And then we tested the using the second derivative test for change of sign for the second derivative. And then, of course, we plotted all those critical points for local minimum and the critical points for points of inflection. You see how the curve now occurs this way because it's concave up to the left of 0, concave down from 0 to 2. So from 0 to 2 it's concave down, that's why it looks like this. And then to the right of 2 it's concave up. And where we have a local minimum where the derivative there is the first derivative is 0, that means you have a horizontal tangent line, and then it's concave up, that makes it a local minimum. Again, just to remind you, to find the critical points, you plug in the critical values into the original function y. Do not plug it back into the first derivative or second derivative. You plug it back into the original function.